Okay, so we might as well get started here. So today what we're going to go over is we're still reviewing traditional combustion. And so we discussed chemical equilibrium, thermodynamics, a little bit about chemical kinetics. And now the last piece of the puzzle that we need to put together before we can get to the governing equations, which will start on Friday, is transport phenomena. And so this is transport phenomena is extremely important for combustion. And what I mean by transport phenomena is really transport uh, at the molecular level. And so this is just due to the random motion of molecules, basically mixing molecules that have different properties. And so just consider this diagram here where we have initially in a box, you could consider this in a box. We have orange molecules and blue molecules. You could say that they were separated by a partition. And then at time equal to 0, we basically let this partition go and then observe what happens to these orange and blue molecules. And these orange and blue molecules have different properties. Aside from their color, they could have different temperatures. Because they are orange and blue molecules, you could define a concentration of orange molecules and a concentration of blue molecules down here. There could be a net tangential bulk velocity of the orange molecules that is different than the tangential velocity of the blue molecules. Uh, and so and so these orange and blue molecules can all have these different quantities. But now at the molecular level, these all these molecules are statistically never stationary. They are always sort of fluctuating about randomly. Okay, and so because they are fluctuating about randomly, what's going to happen is the orange molecules are going to randomly walk down, and they're going to sort of meander and migrate down into the blue molecules, and the blue molecules are going to sort of randomly walk and migrate up into the orange molecules. And if you let this go for a very long time, eventually the system will become perfectly uniformly mixed with the orange molecules and the blue molecules. Okay, and so that process where these different molecules are being mixed and transported around at this really zoomed in molecular level is called molecular transport. And along with the identity of a molecule, these blue molecules are transporting their temperature, their concentration, their velocity, etc. Okay, and so this random motion it not only makes the concentration of the particles uniform, but it also transports their properties along with the particles. And so, if we were to not just basically track the mass of the blue molecules, say moving up, but if we were to track the momentum of the particle or of the molecules, you could derive actually from first principles and using the kinetic theory of gases, and I'll discuss that very briefly. You can actually derive from first principles Newton's law of viscosity. And so if you keep track of the mixing of the two different of the different velocities of the blue molecules and the orange on in the orange molecule, you can uh, you can derive a basic theory to actually predict very accurately for gases or for dilute gases. You can derive the viscosity. If you account for that these molecules can have different energies, just say different sensible energies or different temperatures, and you keep track of that as these molecules move about, uh, you, you can derive expressions for the thermal conductivity, and from first principles, you can derive Fourier's law of heat conduction for gases. And then also, there's a third one, and and then that is the mass of, say, if we keep track of the mass of species I, or the mass of the blue molecules, and then keep track of their mass as they move, as the blue molecules migrate up, uh, you wind up with something called the mass diffusivity of species I, and I will discuss that in the following slides. And you wind up from first principles deriving the so-called Fick's law of diffusion. Okay, and so technically, I don't think these should be called laws anymore because they can be derived from a more general principle. But I think the term law is still used for uh, uh, historical purposes. Okay, and so this is the sort of gist of this. This gets extremely complicated to do it accurately, and there are specialized folks who spend their careers doing just this. And so, why this molecular transport is very important. You may think that in a propellant or a rocket or a detonation, that basically all these tiny little molecular processes don't really matter. I mean, you know, like, who cares? Is that it is important for most combustion. Basic detonation theory is one notable exception to that, and you will understand why after we get done with the discussing detonations. But basically, mass diffusion is as I said before, is the molecular mixing of different species of different gases. So let's consider a normal torch. So a normal torch here, you have a fuel injector. You are basically shooting. You are injecting fuel into the system, and then outside you have air. And if you ignite it, you'll have a nice little so-called diffusion flame. Actually, the term diffusion flame is becoming out of vogue right now. The term is non-premixed flame, because you can have because non-premixed is the more general term. You can have non-diffusion dominated non-premixed flames, and I'm not going to get into those in this class. But now there's a question here: is that at the fuel inlet, you have all the fuel over here, and you have all the air over here. And so the air and the fuel aren't mixed. So how do you have a flame if the fuel and the air are not mixed? Well, basically, at this boundary where the fuel and air meet, all of these really molecular scale transport processes are mixing the fuel in the air. And then after those molecular transport processes mix the fuel in the air, then if there's a heating source, which can be the flame itself, if there's a heating source, that mixed fuel and air can then burn and react chemically. Okay, and so these transport processes are extremely important for combustion. And if you consider what's called a premixed flame, and that could be a standard Bunsen burner, where instead of just pure fuel coming out, you have a mixture of fuel and oxidizer. And so this mixing process that I talked about here, you basically no longer need to do that. But still, molecular transport is still extremely important here, because you need to think that if you guys have used a Bunsen burner and you get this nice sort of conical flame, and it's nice and steady. But what is causing that conical flame to be nice and steady? You have a jet of premixed oxidizer and fuel coming out, and there's a nice conical flame. Well, so something is heating those cold reactants up to a temperature to where they can react chemically very, very rapidly. And it turns out, and after we discuss per, pro, propellant deflagrations, you will actually understand this very, very clearly. Is that what is transporting heat to the cold reactants is heat conduction from the high temperature products down to the cold reactants, and heat conduction is a molecular process. Okay, and so these processes, even though you can have supersonic flows, things like that, these sort of very, very small scale processes of molecules themselves plays a role not only for chemical reactions, but also describing how these different molecules mix and interact with one another. Okay, are there any questions? Okay, so I'm going to describe a sort of phenomenological theory. I'm not going to do any real calculations with this. In the other combustion class, we do, but the kinetic theory of gases can be used to derive, as I said before, rates that arise from the transport of molecules, including Fourier's law, Newton's law of viscosity, and Fick's law of diffusion. And so a really sort of simple way of sort of conceptualizing how this process works is that we basically pick a plane here. This plane is at basically height z, and we want to find the net amount of a property of a molecule. It could be the energy, it could be the mass, it could be the momentum, etc. And we just pick this plane, and we want to find the net amount of transport of that quantity through this plane. Okay, so as I said before, we basically pick a property, mass, energy, momentum, etc. And then we use results from statistical mechanics to basically estimate the net transport of the molecules, basically moving up through our plane from the bottom. And also we have the blue molecules that are net migrating up through basically through this plane. And we can use statistical mechanics to actually to basically very crudely estimate that. And we have also orange molecules that are migrating down from the top on net. And so we can use statistical mechanics to basically basically estimate the net flow of these orange molecules down from the top. Okay, and so basically we pick a quantity, and we basically play a big counting game and just count the number of and then count the amount of that quantity, say the energy of a molecule, basically moving up through the bottom and also down through the top. And so and so that's the basic idea of basically how this works. And so here we are here, since I got orange and blue molecules, I am tracking the mass of, say, the blue molecules. So I basically have a mass fraction gradient of the blue molecules. So I have a higher mass fraction of the blue molecules down here, and a very low mass fraction of the blue molecules up here. And so using this theory and just defining a gradient, you can actually compute a net transport of the blue molecules up from the bottom. Okay, and so that's the basic idea of how this works. I'm not going to go through the derivation in detail. It takes about a lecture and a half. And at this point, it's just for this class we only care about the end results. But you can use this sort of simple idea to derive Fourier's law for gases, Newton's law of viscosity, and Fick's law of diffusion. Okay, it's just a matter of which property you pick to basically tag along with either the blue molecules or the orange molecules. Okay, and so Fourier's law, you guys, at least the mechanicals, have dealt with this in heat transfer. And this isn't, and as I said before, this is very important for flames. It's also important for if you're working with an engine or a gas turbine, you are really, really concerned about heat transfer, heating things up, say turbine blades, things like that. And so I will define the conduction heat flux, a Q dot double prime, and I'll just use a subscript cond for conduction because we have other forms of heat transfer that we need to consider. And so that's just equal to minus of the thermal conductivity times dt dx. This here is straight up Fourier's law in one dimension, and if I'm generalizing it to a multi-dimensional flow, it is minus the thermal conductivity times grad T. And I know in your heat conduction classes, thermal conductivity was traditionally K, but in combustion, it's traditionally lambda. Okay, and so you guys, I think most, if not all of you, should have seen this before. So I'm not going to belabor this point. Now, here we have a mixture of a whole bunch of different gases. And so there's a bit of a problem here is that we need to determine, we just want one lambda, and we need a mixture averaged thermal conductivity. And there's no really good theory for doing that. So there's a lot of empirical mixing rules. And so if you have a mixture of different gases, the most common one that you see used in combustion is this one right here, where the mixture thermal conductivity is just 1/2 of the sum of a mole fraction weighted thermal conductivity plus the sum of 1 over the sum of xi over lambda I. Don't ask me how they came up with that one. There's another empirical one. I use this one because it is quite a bit cheaper. It doesn't have these two sums. And this is just this is a power law weighting rule. And Aaron and Giovangeli, they did a very intensive study and found that basically this simple mixing rule here in a lot of different scenarios is actually more accurate than basically this mixing rule here. And I'll briefly mention what it is, but there is a very rigorous way to get this, to get the mixture average properties. But it's extremely expensive and no one and few people ever use it. Okay. And so again, this should look familiar to you guys with the exception of perhaps how you compute a mixture average thermal conductivity, because you could have, say, 200 different species of gases, and they could be at random pressures and temperatures. So that means you can't just go to the book and then basically look up what the thermal conductivity is for that mixture. You have to compute it. Okay, and I will briefly discuss how to compute these mixture averaged or the species specific thermal conductivities later on. Okay, a viscous stress. Actually, this is not important for flames, but important for fluid mechanics, fluid flow. And so, if you have boundary layers and things like that, those can have a substantial effect on combustion and then also turbulence. And so, again, this is Newton's law of viscosity right here, where basically the shear stress is equal to the shear or dynamic viscosity times du dx. This is Newton's law of viscosity. And you guys who have had Fluid Mechanics 1, you know that, or even a more advanced course in say, fluid mechanics, that the shear stress in general is for a fluid is given by this. and I'm not going to get into the derivation of this. You have all kinds of classes that sort of get into this stuff. And this here is a bulk viscosity kappa, and that's normally assumed to be 0. Okay. And because we deal often with say compressible flows, this divergence of the velocity vector is definitely not 0. Okay. And if you want to compute a mixture averaged a shear viscosity, the so-called Wilkie formula is very commonly used, where it's this crazy sum inside of it's a sum inside of another sum here, and you got this really sort of complicated phi ij term that you need to compute. But codes like Cantera and Chemkin and things like that basically mix the viscosity off of this. And Aaron and Giovangeli have basically deduced this empirical mixing rule here, and that seems to work well enough, and you don't have a sum of sums. So if you have 200 species, you have 200 times 200 terms to sum. This is extremely expensive, and you do not want to do that huge of a sum. It just gets to be astronomically expensive. And so if this is off by, you know, like a few percent, you know, who cares? Okay. So are there any questions? Okay. So this stuff, with the exception of the mixing rules, should have been all stuff that you've seen before. Okay, so now what a lot of you have not seen before is Fick's law of diffusion. And this relates the diffusive mass flux. Oops. Flux of a molecule to the gradients in concentration. And so Fick's law, basically for a flame, it will mix the fuel and oxidizer at the molecular level. And so if we consider a mixture of species A and B, I'm just going to call them A and B, the diffusion mass flux m dot double prime A of species A is minus rho times a diffusion coefficient DAB times dya dx. So this here is actually called Fick's law of diffusion. And Fick's law of diffusion is analogous to Fourier's law for heat conduction, but instead of mass diffusivity here, you would have a thermal you would have a thermal diffusivity here. Okay. And in many ways, mass transfer this is called mass transfer. In many ways, mass transfer and heat transfer are analogous phenomena. And in fact, they're so analogous that usually the last chapter in heat transfer or in your heat transfer books at the undergraduate level is a chapter on mass transfer. And essentially, they basically say that all of the correlations, all of the conduction, mass transfer, etc., are all the convective mass transfer, all the stuff that you studied for heat transfer directly applies to mass transfer with a few caveats, of course, because it is different physical phenomena. So there are some differences, but because the underlying driver of mass transfer has a very similar functional form to heat conduction, there are a lot of analogies between mass transfer and heat transfer. And in multiple dimensions, this is just given by minus rho times a diffusion coefficient times the gradient of the mass fraction. Okay. And
so
DAB, yeah, go ahead.
I just have maybe a comment of how I could think of how these might be different in my mind at the molecular level, because at least, in your conduction course, you think of things as, maybe two solids sitting next to one another exchanging heat, where now we're talking about a bunch of billiard balls bouncing around. And like when mass diffuses, now you just say have more molecules in one area. And then when heat diffuses, and if we define temperature as the average temperature, yeah, your average temperature may go up. But when we're talking about producing a flame, you need, you know, particular molecules to get to a certain activation temperature, right? And so are we talking about a molecule specifically giving some of its heat to another molecule that's at a lower temperature, which would require a collision of those two molecules? Or am I thinking about that wrong?
No, you're thinking about that right, but there are other effects too. Is that you have these molecules here moving up, and they are banging into the orange molecules. Say that the blue, say that the blue molecules have a temperature of 1,000 Kelvin. You know, if you could define a temperature for basically one molecule, you can't really, but let's just pretend you can. And you have a temperature of an orange molecule at say 300 Kelvin. And yes, they do bang into one another, and they do transfer energy that way. However, that tends to be a smaller effect than basically just the blue molecules moving up. Okay, and so basically most of the effect is just that these blue 1,000 Kelvin particles are basically 1,000 Kelvin molecules are basically moving up almost freely. And this sort of collisional effect, which is accounted for in more advanced theories, is also an important player. But the primary effect is just the fact that basically these blue molecules are just moving up, and they are carrying their temperature along with them. And because the temperature and their mass are being carried up together simultaneously, basically mass diffusion and heat conduction are analogously similar. And now for a solid, you can even play this sort of game, this sort of molecular game, in the sense that, but instead of basically molecules freely moving around, all the molecules are attached by springs. And so basically all of the heat conduction and things like that are basically molecules that are attached by springs or basically vibrating around. And yes, you do have mass diffusion of two different solids. It is extremely slow. It takes forever, but it does happen. Like if you had 1,000,000 years and a piece of copper and a piece of steel, even in a non-oxidizing environment, they would eventually, you would have a layer of mixed steel and mixed copper. It would take a gigantic amount of time though, but it does happen. Okay.
Thank you.
Yep. No, that's a very good question. Yeah, because, and also all this detail with the colliding molecules and how they collide. When I show you the real formulas for basically mass transport, they get extremely complex for those reasons. Okay. Now, one thing to note about mass diffusion is it does not induce any bulk motion. And that means there is zero net mass transported by diffusion. So if I go back to this cutting plane, that statistically for every blue molecule that is moving up, there is an orange one that is moving down if the total concentration is the same on the top as it is on the bottom. Okay, and so that means there is no bulk fluid velocity that is induced by mass diffusion. Let's see, where am I at here? And so if we define, if we force the diffusion mass flux to be, we can prove that is the case. If we just consider two species, and we apply this formula here, for two species, Dij and Dji are the same. So we can basically pull this out and then basically sum them up. And I can, since the gradient and the sum are two linear operators, I can move this sum inside of the gradient here, and I have the gradient of yi plus plus yj, and I have two species, and by definition, the sum of the mass fraction of species I and the species j, it has to be 1 by definition. So I'm taking the gradient of 1, which is a constant, and the gradient of a constant is 0. And so basically that proves that at least for two species, and you can generalize this to a mixture of basically n different gases that have different diffusion coefficients, but you need to use that more advanced theory to do it, and we're not going to play with that in this class. Okay, now in combustion, what is traditionally defined is a diffusion velocity is not to use Fick's law directly, but to use what's called a diffusion velocity. And so what we do is we define m dot double prime to be equal to rho times y. I don't know why I always write down to the basically down as my iPad pencil moves to the right. I don't know. It's just the way they're all tilted down a little bit. It's just interesting. Anyways, you define the diffusion mass flux as being equal to rho times the mass fraction of species I times a diffusion velocity. Okay, and so this is just a definition, and this has to be equal to our result from Fick's law of diffusion. Okay, and so Fick's law of diffusion defined this to be equal to minus rho times the diffusion coefficient times the gradient of yi. And basically this is equal, and we basically set this equal to the definition above and solve for the diffusion velocity. And so this diffusion velocity is just basically v is equal to basically minus dij over yi times grad yi. Okay, and so that's just a definition. It is very commonly used, and the reason it's very commonly used is that there are all kinds of different models for this mass diffusion. Fick's law itself is rarely used directly because it isn't very accurate if you have a whole lot of different species that have all these additional effects, as was brought up earlier. And so this is just a way of generalizing that you have mass transport, and then basically you can insert your model here. If you have Fickian diffusion, basically this is what the diffusion velocity is here. And so in the following slides, if I use I'm going to drop this underscore diff. If I have a cap v, it is referring to the diffusion velocity. Okay. Now, one thing we need to consider is that along with the mass that's being transferred during diffusion, there is also energy that is being transported, even if the temperature of the blue molecules and the orange molecules is the same. There will be zero heat conduction flux. There can still be a net energy being transported across our plane here. And what's causing that is the fact that the enthalpy of formation, or the chemical energy of the blue molecules, might be different, and in fact, in general, they are different than the orange molecules. And so if we account for this net energy that is being transported across this sort of cutting plane here, there will be a net energy transfer that is being transported along with the molecules, even if the temperature of the blue molecules and the orange molecules are the same. This here is called, as I said before, it is called the interdiffusion heat flux. And so I'm just going to call this q dot double prime diff. This here is just the sum of m dot double prime I, or the diffusion mass flux, times times the enthalpy of species I, where basically HI is just the partial molar enthalpy divided by MWI. And so this is the same partial molar enthalpy that you guys worked with on homework 1. Okay, and so that's and the reason I had you do that problem is every now and again I come across a paper doing supercritical combustion, and they use, say, the Peng-Robinson equation of state. And for the interdiffusion heat flux, they just use the ideal gas term, and they do not properly use the partial molar enthalpy. Okay, so it's a very common mistake that, or it's a mistake that is more common than it should be. Okay, and very commonly this term here will not be written in this form, but you'll directly use the diffusion velocity, and it will be written like this. So it'll be the sum of yi vi times hi, where again hi is related to the partial molar enthalpy. Are there any questions here? Okay.
So does this have anything to do with equilibrium? Does it try to match the enthalpies? Because that's just a pressure that I'm just trying to figure out if there's a, if you release two species, how you could guess, what the mixing is going to look like at, we'll call it like a steady time later. Can you, I guess, predict that based off of the enthalpies of formation, trying to balance in a volume, or I guess maybe
no, because basically this
moving.
term here literally comes from just the fact that there is net transport of, say, blue molecules moving up from the bottom, right?
Right.
Okay, and now at equilibrium, the concentration of the blue molecules will be the same on all three of these planes, right?
Right.
And so that means since the concentration will be the same statistically for every blue molecule that is moving up from the bottom, you have another blue molecule that is basically that is moving down from the top. In such a scenario, the diffusion velocity will be 0. And so basically this term here basically will be 0.
Gotcha. But so from an entropy perspective, there is no exchange, or there's no change in entropy from any given state, because there's not one state that is more.
Oh no, there is a huge increase in entropy from the initial state, like this. As we go to the final mixed state, there's a huge increase in the entropy, and that's called the entropy of mixing.
So I guess, okay. So then there's some point where you could split that volume in half, and you would assume that the concentration is balanced on each side, and that would be the final mixing state?
Yep. Yep.
Okay.
Yep. In the statistical sense. Yeah, and that entropy due to mixing, you guys, I did not specifically bring it out, or I didn't call it out, but if you remember in the ideal gas Gibbs free energy, you had this log of the mole fraction times the times the pressure over a reference pressure. That term is an entropy increase due to mixing. Because if you consider, in this case here, that term, if you compute that term for the blue molecules here, that extra term will be 0, because, say, the mass fraction here is 1, and so that term just goes away. And here that mass fraction term is 1, so that goes away. But here, those mole fractions are, for both species, are not 1. So you accrue that sort of log term, and so that is an entropy associated with mixing. And basically, this state here, and it's saying that this mixed state here is in a higher state of disorder than in this highly separated state here, and that basically, because the entropy here is higher, all of these molecules here, they can't spontaneously unmix. If you want to unmix them, you need to somehow, with the hand of a deity of your choosing, go and take the blue molecules, like say by hand, and physically move them down yourself. So you need to put work or heat into the system to get that to occur. Okay. Okay. So yeah, and so but basically all of these processes, even shear viscosity, is just due to basically the properties of these molecules moving up through the top, and also down through the bottom. I mean, up through the bottom and then down through the top. Okay. Now, but as was mentioned before, this theory does not account for the collisions. So basically, this blue molecule here could be bumping into this orange molecule here, and that changes the net flow of the molecules through this plane. Okay, and so more advanced theories are based on the Boltzmann equation itself. I'm definitely not going to get into that in this class. And these predict much more complex diffusion theories and additional terms. This is called, it's called by several names, Stefan-Maxwell diffusion, a multi-component diffusion, or basically sometimes just the Stefan diffusion. Okay, and essentially, here I will, what this basic theory does is it relates gradients and mole fractions to the diffusion velocities. And so here is the final nightmarish expression if you want to use the full Stefan-Maxwell formulation. So here we have the gradient of the mole fraction is equal to this more complicated Fickian diffusion term that's based on the diffusion velocity for species J minus the diffusion velocity for species I. This here is so-called pressure gradient diffusion. It's called barrow diffusion. It's normally neglected, but if you have a massive shock wave and a massive and a mixture of light and heavy molecules, and in that case, you have a substantial difference between the mass fraction of species I and the mole fraction of species I. You need to worry about barrow diffusion. There's a term here called Soret diffusion. I will discuss that a little bit later on. It's not fully well understood as to what caused that. It's a so-called second order term, but it is the transport of mass caused by temperature gradients, and it is really weird. And there's also an additional unequal body force diffusion term. This normally for traditional combustion, we don't need to worry about this. But you could get such an effect here because for us, about the only body force that we have to deal with is gravity, and the gravitational acceleration is the same for all of the molecules. So ergo, this goes away. But you could say but if you have a plasma, you could have some species that are charged and some that are not charged. And so the charged species could be subjected to say a magnetic field, while the uncharged species are not affected by the magnetic field. So in some extreme applications, you need to worry about this, and then that can cause some species to separate from basically different species. And these DTs here are called the thermal diffusion coefficients. I'm not going to get into how those are computed. Again, that's part of this really complicated theory. And so this here, again, just take it as an expression that was given to you by your friendly local physicist. But okay, and then you can do the same thing for the heat flux. That is not nearly as complicated. If you use the more advanced theory, you get the traditional heat conduction term as is. You get this interdiffusion heat flux, as I said before, and that's just due to the energy that is being carried with basically with the species as they transport. And we have the so-called Dufour effect, and that is an energy transfer due to basically due to mole fraction gradients, and where basically this di here is called a diffusion potential, and it's just given as the gradient of the mole fraction plus basically plus this barrow diffusion term here. Oh, and I should say that one thing that makes this expression difficult to use is that it is not explicit in terms of the diffusion velocities. You need to solve a system of linear equations to basically back out the diffusion velocities from the basically from the mole fraction gradients. Because because at any point in space you would know the mole fraction gradient, you know the pressure gradient, you know the temperature gradient, etc. And so you could compute all of the terms except for the v's, but all the v's are related to one another. So you would in turn need to solve a system of linear equations, and so it gets fairly complicated, but it's very accurate theory. Okay, let's see. And so apparently my internet connection is unstable, but the Soret and Dufour effects are so-called second order diffusion effects. They're sometimes called cross diffusion, although cross diffusion can mean something else completely differently. So I prefer to not like that term. And so the Soret effect is mass transport caused by temperature gradients. And again, for gases, it's not really fully understood as to what this is. It's just a term that came out of a very complex theory, but it is important. And so the Soret effect is similar to thermophoresis for first-state small particles. So here I can draw a picture and sort of explain that. So let's say we have a big particle here. It could be on the order of, let's say 10 to 100 nanometers. And I have some molecules here. The concentration of the molecules is the same on both sides, but there is a temperature gradient. So the temperature is higher here than it is over here. And so what happens is the higher temperature molecules have an on average higher velocity. And so these molecules are going to actually collide with the front of this particle. But because their temperature is higher on this side, you're going to have more collisions, and the collisions are going to be more energetic than the collisions of the molecules on the backside of the particle. You're going to have fewer collisions because the molecules are on average moving slower, and they're not going to be as energetic. And so there's an imbalance of basically the impulse generated on the particle on the front than there is on the back. And so this particle will basically move with the temperature gradient. And so that is called thermophoresis. And the Soret effect is sort of extremely hand wavy, is a version of that for molecules. And so that's a very hand wavy picture of that. But you could at least in the case of thermophoresis or for particles, you could sort of picture what it is. The Dufour effect, I cannot picture what that is. It is a heat flux caused by mass transport, and I will leave it at that. It's a crazy second order term. And these effects are normally, the Soret and Dufour effects are often neglected, but they can be important. For traditional combustion, they are important if you have mixtures with light species such as atomic hydrogen, basically helium or even hydrogen. And so you will often see the Soret and Dufour effects being included for hydrogen combustion. Whereas if you're doing methane combustion or endodecane or something like that, or diesel fuel, or jet fuel or rocket fuel, you often don't need to consider that. But for really high pressure applications, that is, some folks say you do need to include the Soret effect, and some folks don't. But in most cases, it's really expensive to calculate from a computational standpoint. And for most combustion applications, it normally doesn't add very much accuracy. And so you just forget about them in most applications. But if you are studying hydrogen combustion, then it is traditionally included. So I guess that's it for today. Do you have any questions?